Welcome to this video. In this video I will prove or derive the derivative of sine and cosine. I will do this using four core identities, which are like trivial results from the complex exponential function. The first identity is the MacLauren series for the sine. All right. So that looks like this. Sine of x is equal to the sum of a bunch of terms, which have an alternating sign, and then the value of the terms themselves are going to be these odd powers of x divided by the same power factorial, okay? And this comes from the it kind of looks like the MacLauren series for the exponential function. That is because they're extremely closely related. All right. So if I write out the first few terms, oh shoot, oh this is true actually. Sorry, my bad. So when n is 0, we get just x, then we get x squared over 2 factorial plus x to the 4th divided by 4 factorial. Then minus a bunch of minus and plus alternating a bunch of terms. Okay, beautiful. All right. And then we take the cosine of x, which is pretty similar. Let's give it a little bit more space. Cosine of x here, and that's going to be the sum. Similar sum, and from 0 to infinity, an infinite sum. We still have alternating terms, but now we instead of taking the odd powers, we take the even powers, which is even simpler because we don't have that nasty +1 there. So cosine is much nicer in this respect, but it's going to be more annoying in other respects. Oh shoot. Sorry about that. These are, of course, the odd powers. This is going to be to the 3rd and 3 factorial, 5 and 5 factorial. There we go. All right. And now the cosine is going to be the even powers. And this makes sense because cosine is an even function and the sine is an odd function. Beautiful. Okay. All right. And we can also see then if we put x equal to 0, all these terms cancel. We just get our beautiful 1. And the same with the sine. Don't give 0 if x is 0. Wonderful. Okay. The next two identities we need are the sine and cosine of a sum of two numbers. All right. So we have the sine of v plus w is equal to the cosine of v sine of w plus the sine of v and the cosine of w. All right. I don't remember this by heart. The way I do this, I just remember that for the complex exponential function on the unit circle, adding numbers is basically the same as taking the product of two complex numbers, and so this is going to be like a cross product where you take the imaginary parts. You can find that on one of the other pages, I think. Beautiful. Let's do something similar with the cosine. Yes. So this is going to be the real part. So that's going to be where we take the cosines and multiply them together. But then we take minus the sines, and that minus comes from the I squared because we're multiplying two imaginary parts, which will give us an I squared here. All right, but luckily it cancels, and we just are left with this nice real expression. Beautiful. And all these results come from the complex exponential function. All right, where we take the imaginary part, we take the real part, and as you can see, is these are all the terms of the complex exponential, the exponential function, just with these alternating terms, and these alternating terms come from the different powers of I. So it all makes sense. This is the core explanation for all these results. So in that sense, I think this proof really becomes beautiful. That it basically stems only from this one result. All right. All right. So the statement that I'm going to prove with these is that if I take this sine and find the derivative, I'm going to get cosine. And if I take the cosine, find the derivative, I'm going to get minus sine. It would have been so beautiful if these were equal, but that only applies for the hyperbolic trigonometric function. In this case, we're going to get this minus, but it's interesting, and it gives us a different set of differential equations that we can solve this and stuff like that. So that's, I don't mind that. Beautiful. Okay, so that's our statement, very informally, but I don't want to take too much time in writing a bunch of stuff around this. So let's just start with the proof. All right. So we do our, we make our secant slope. Okay. So we do our secants. We take the rise and overrun, and then we take the distance between the 2 points and have it approach 0. Okay. And then we have our derivative if it's differentiable. Right. All right, so let's start with the rise, so to say. So I take x and I add this little thing. So I have the x and another point that's a little further off, right? And I take the sine of the x. Okay, so the difference between the function value at these two different points. So this is the rise, right? All right. I use this this third identity here. I use this identity to rewrite this first term here, okay? And what I get is, I get the cosine of x sine of h plus the sine of x cosine of h. And we have to subtract that last term there, sine of x, right? All right. We can see that there's a common term here. There's common factor. This is a factor in this term and in this term. Okay, so let's do what we always do with common factors. We extract it outside of a parenthesis. All right, so this will just stand. And then we get this common factor, and what's left in the first term is just the cosine of h minus the 1 there. Beautiful. All right. So to make to find the derivative, we have to take this rise and we have to divide by the run. We have to divide by the distance between these 2 points. Right. So we do the same thing here. And we do the same thing here. All right. And now what we do is we do this beautiful thing. We take the sine of h and we replace it by this expression. Right? And so what we'll get is, maybe I'll move this a little bit further back here. This is the same equality here. I think I'll need a little bit more space. And I'll get cosine of x here. And then for the sine of h, we will write this thing. Right? So it's going to be an h minus an h to the power 3. And then the 3 factorial plus h to the power 5 divided by 5 factorial minus boom, boom, boom. There we go. All right. And then we go plus sine of x. And then we take cosine of h minus 1. And what happens is this 1 here from this expression will cancel. So we'll just lose this. We write all the other terms that include an h. Right? So we have minus h squared divided by 2 factorial plus h to the power of 4 divided by 4 factorial minus that. There we go. And we still need to divide by h. But dividing by h is so beautifully simple now because look at these terms. What happens if I take h and divide by h? Well, I'll just get a 1. If I take an h to the third, h cubed, divide by h, I get h squared, and so forth. All these powers just reduce by 1. And when I have h, distance between the points, approach 0, this whole term, this whole factor, will simply approach 0. What happens here? Well, nothing happens to the 1, but all the other terms will cancel, and this whole thing will approach 1. And what I've shown now is the derivative of, let's change this to an arrow, for h approaching 0. The derivative of sine is cosine. Beautiful. I could remove all this and then do the same thing for a cosine, but the argument is so similar that I will just adjust this to fit. All right? So I will replace. If you need to read this further, or if you need to study this, just pause, and then you can resume it when you're done. So I'll change this to a cosine. I'll change this to a cosine. Boom, boom. All right. Now we use the second, or the last identity here, and we'll get 2 cosines here. We get a minus here, and then we get 2 sines here, and a cosine here. All right, beautiful. So what happens now? The exact same thing. We have a cosine here, and we have a cosine here. We have a common term, right? So we'll do the same thing as we did here. We'll put the cosine outside of a bracket, parentheses, whatever you want to call them. The only difference is what's left, what we've not touched, is now going to be a sine. And not only a sine, it's going to be a sine with a negative sign. Oh, it sounds weird. Sine with a G. So it's a minus sign here, right? Because there's a minus here. All right, beautiful. Okay. And now the argument is the exact same thing. This whole cosine of h minus 1 will approach 0, and this sine of h divided by h will approach 1. And that means that the derivative of cosine is going to be minus sine. Isn't this a beautiful proof? I really love it. And it all stems from this beautiful complex exponential function. And everything just falls into place. You don't need to make some complex calculus argument for why sine of h divided by h is 1. It's just a simple consequence of the MacLauren series. If you have any comments or questions, feel free to put them in the comments. Not because I'm trying to promote the channel, it's just I'm just curious to hear what you have to say. Have a nice one.